Next, I'm delighted to welcome David LeBlanc from Terrestrial Energy in Oakville in Canada. Terrestrial Energy, who was one of the first movers in the molten salt reactor space. And David, I'd like to invite you to talk about the integral molten salt reactor.
I'll get underway. I do tend to go fast when I'm allowed to speak technically. I get quite excited and lots to talk about here. Very quickly, Terrestrial Energy, we're, as John mentioned, we've been in the game. Well, we've been a company for just under 10 years now. I've been in the sort of game itself for about 25 years. We are a private company. We've raised over $100 million private funding, some government support. As well, we are an engineering firm over. Sorry about that. Just over 100 people, mostly scientists and engineers. It is truly an engineering firm. We are very early. We got into the regulatory process, pre-licensing applications, etc. So we're operating within a regulatory framework. That's a very different, very different. Field to be in. We tend to try to operate within the rules, not trying to get either the regulator in Canada or United States to change too much. I'll speak more about this, but sticking to where possible, conventional design, conventional heat exchangers, etc. But very quickly, there's many different vendors on the line, different approaches. We're trying to stick as much as possible to original development, what has been looked at, what has been worked on, what has been proven, etc. So we're sticking with fluoride chemistry. I'll speak a bit more about our fuel cycle, but using standard assay low enriched uranium, so under 4%, using graphite moderation for the thermal spectrum, like in the molten salt reactor experiment. Again, borrowed a bit from Oak Ridge development, looking at an integral core arrangement architecture, and I'll explain a little bit more about that. But the development kind of tree, the molten salt reactor experiment, we really feel was a great demonstration of the technology. Some of the last work at Oak Ridge in the early program around 1980 was on using these as just using low enriched uranium, and that's kind of what's led to us. So very quickly, what I feel is kind of the innovation, but the pragmatic innovation of the IMSR, we're looking at a roughly 7 to 10 year time for what we call a core unit replacement. So we have the graphite in the reactor, which we'll show in a minute, but that is along with our heat exchangers. So we're replacing that unit on a 7-year cycle. That really helps with the qualification of metals. Many have talked about corrosion. We're working hard on that issue as well, but our metals in contact with fuel salt only have a 7 to 10 year lifetime. We have, for now, chosen a very inexpensive carrier salt that avoids the tritium production of either lithium or beryllium. And but when lithium-7 is commercially available, when we have better handle on tritium management, that could be a fuel of our future. For now, we have a similar fuel economy to boiling water reactors, but with planned evolutionary advances, including, as I mentioned, eventual use of enriched lithium. And that can bring your fuel economy down to a small fraction. I'm talking about uranium use for compared to PWR. We feature passive decay removal, featuring a closed cycle natural circulation. I won't have time to get into many technical details. We really design, though, with a very strongly negative temperature coefficient, and all our inherent terms are negative on their own. That means we can get by without control rods, and we have a passive shutdown case. We do have shutdown rods, but they're not credited for safety. That is very unique, and it's anyway, something that we've been discussing with the regulator for many years now. The graphite allows a very soft spectrum, very low enrichment, around 2% to start, and it allows us to use a makeup fuel of 5%. That is an enormous difference. Almost every advanced, Gen 4 reactor will need either high assay LEU or recycled plutonium, etc. High assay LEU is simply not commercially available. Massive relicensing of facilities, etc. Very long time horizons and very expensive for the other Gen 4 reactors. And another innovation, we partially reuse fuel salt between core units, and that really saves on volume. Very quickly, the IMSR plant works. As I said, it's an integral pool within a can, so to speak. We have our heat exchangers. We've gone to a radial flow heat exchanger, makes things a little taller, but we like other aspects of it. But graphite moderator in the bottom of the core unit. So the fuel salt stays within that core unit. A makeup fuel salt is trickled in over the 7 years, so there's a slight rise in the level. A secondary clean fluoride salt, the potassium fluoride, zirconium tetrafluoride, removes the heat from the reactor, and we've chosen to go to a third loop, a nitrate loop. Many others are also proposing nitrate loops now. That gives us a great interaction with either making steam for power generation for industrial heat uses, also solar salt, of course, involved in thermal storage for balancing out grids, etc. And really good coupling with industrial heat uses, either directly as the solar salt or intermediately providing steam. And that's really where we've focused our development of late, is in industrial heated power. We don't have time to get into too many technical details here, but we have operating silos. We have what you call a switch loading arrangement, where one is in operation and allows a use unit some cool down time before the core unit is moved within the building, within the reactor auxiliary building, to storage silos. So the important part here is nothing radioactive needs leave the building itself. The excess fuel salt is stored in tanks. You can see between the two silos, and our spent core units are stored within as well. Molten salt technology gives you a lot of advantages in general. Molten salt's high in thermal stability, neutron stability, high heat capacity. That can lead to higher revenues. We're operating at 50% greater thermal efficiency compared to light water reactors because of the higher temperature. That means more revenue, more profit. We, like other molten salt reactors, not using high pressure systems. That substantially simplifies your plant, smaller plant, etc., and more financeable in general. And those same product properties really allow you high inherent safety. We can deal with a substantially negative temperature coefficient, fluid convection, the fact that a liquid can conduct, etc., really helps with decay removal. So it gives us a stronger social license. I have a chart here that just try to compare. SMRs are kind of a buzzword these days, but just making something smaller. Yes, modularity will help you, but the folks went to 1,000 megawatts or 1,500 megawatts for a reason. There are economies of scale. So if you just take a light water reactor, try to make it smaller, you're going to start with a penalty. Your modularity can bring that back down, but we really don't think that's going to be enough. It really is about the R in SMR. It's about the reactor. And with molten salts, you're a higher delivery temperature, so that's a great impact on your overall cost, low pressure operation, and then a high inherent safety. We have designed a twin unit, so it's kind of double output. Each reactor is 442 megawatts thermal, capable of 195 megawatts electrical, depending on your heat and or power needs. But we're looking at a twin facility, so kind of double that. We really feel the industrial heat market is a most likely early adopter. Utilities tend to be a little more conservative. We can really beat folks on price and flexibility and so many other ways. But providing heat, we are a high temperature reactor. Folks needing high temperature heat, that's really a prime focus of us. So as many others have talked about, we can integrate thermal storage. We can decouple with your industrial user. The salts or steam can be transported to your industrial site. Some cogeneration numbers here. If all you want is thermal energy, that twin unit can provide about 822 megawatts thermal. That's less than double the number I said, but that's when we use some of our own heat to make our house load electricity. We're supplying that about 585 degrees as either salt or steam at just slightly below that. In furnace heat cost relating to about under $6 an MMBTU. Please remember, though, that doesn't mean that $5 MMBTU gas would beat us, because gas price is not in furnace. When you burn natural gas, 20% of the energy goes up the smokestack. So when you look at the boiler costs and those loss, we can directly compete with roughly about $4 an MMBTU gas. The net efficiency, just over 44%, and that is much, much higher than water-cooled reactors. Our cost estimates to date are $50 per megawatt hour, that's US. Very low life cycle, of course, CO2, small footprint, and again, that very important that we're using standard assay. The markets are pretty obvious for cogeneration. I won't really get into too many details here, but we are a Canadian company. We have increasing activity in the province of Alberta. They have an enormous petrochemical industry, enormous industries in general, just very, very many high temperature heat uses that we're finding very attractive as a company. A little bit about our development. We have, well, just showing some of our contracted partners. This is a global effort, Canadian focused, but global effort of partners around the world in terms of equipment, fuel. Even though we're using only 4.95, we've spent years developing potential contracts, Westinghouse, Oranos, and other, for the supply of our UF4, UF6, etc., to use in our fuel salt. It's a long process, even with standard assay. Research and development, I'll kind of show on the next slide. Well, I'll talk about more on the next slide. Graphite, some of the suppliers and consultants we've been dealing with, and general services. So our R&D program, we have been from an early date within the regulatory process. So we do have a different approach. Many companies proudly and rightly so are showing the facilities they've developed. We know the data we are going to produce or need has to be of the enormously high quality that is demanded by the regulator. We don't feel it was cost or time effective to try to develop our own facilities for this very massive R&D project program. So we have outsourced around the world NRG and NRG in the Petten reactor, Karlsruhe, many different national labs in Europe, United States, some universities, etc. So I won't really get in. This is just showing a bit of a snapshot. A couple of things I want to kind of focus. We're very proud with the work we've been starting with ANSTO in Australia. We really feel they have the best solution for any type of waste. It doesn't matter what you do with a molten salt, you are still going to have waste. Geological storage, they typically worry more about iodine, cesium, other fission products than plutonium. So we all have things to do. And the ANSTO SynRock technology really is a very, we feel a superior way, gives a superior story to other reactors as a way to condition your waste, whatever waste you have, for final geological storage. Another quick focus on our R&D is we're very proud that we have done a massive graphite irradiation program in the Petten reactor in Holland with NRG from 4 different graphite vendors, or different graphites applicable for molten salt reactors. And the main thing has to be very low pore size, under a micron. We have 192 specimens. The way this program works, there's 2 irradiation periods, and during that there's different dose rates. We finished the first irradiation period, and I can happily say I just got a sneak peek at some of the first results just last week. Very great. Anyway, very excited about it. These specimens will then go back in the reactor for a few more years. This has been going on for years. Very expensive, many millions of dollars, but we have great, very usable for the regulator data on our dimensional stability, and we'll have all sorts of properties being measured. So very happy about that. Regulatory process, we may regret talking up so much to the rest of the world what a great system the Canadian regulator has in place, because I believe there's been about 12 different vendors that have at least started and stopped different applications. But we were the first advanced reactor to go into vendor design phase 1 in 2017, first advanced reactor to finish. We are very, very close to the final completion of vendor design phase 2. It's been with the regulator on their side of the fence, so to speak, for a while. Pandemic and personnel. Anyway, we're still waiting on the final report. We're hoping it's going to be very, very soon. We've done some process within the United States, but I won't get into too many details. And the CNSC and the United States NRC chose us as the advanced reactor to look at a collaborative regulatory review. So when we have meetings, et cetera, with the CNSC, NRC folks are either online or in attendance. And we've done some work, of course, with the IEA. That's about it. Just some quick recent developments. We signed an MOU with a Korean company on cogeneration plant development. KBR is a big player in the ammonia space. So a collaborative agreement on both hydrogen and ammonia production. The US-Canadian joint technical review has been completed. And just very recently, TerraPraxis, which is a program about repowering coal project involving Microsoft, MIT, and many other partners, has chosen IMSR as I believe, their first kind of power source of desire for their program. So I'll end it there and take any questions.
David, that's really great. Thanks very much. Maxime, do you want to open the floor up?
Yeah, so in this first question from Zuzana, who asks, how much does use of waste heat from the MSR increase its efficiency factor? Could you give an estimation of energy saving by utilization of the waste heat in synthetic fuel production?
I am trying to understand that question.
Can you
maybe
read
if Zuzana is on the call,
pardon?
If Zuzana is on the call, maybe this person can clarify the question.
I'm sorry, I'm not sure if I'm able to make it more clear. I'm just wondering, you were talking about 40% additional efficiency, I think you mentioned, thermal efficiency.
Yes.
And it could be used in order to save energy during, could it be used to save energy during the synthetic fuel production?
Well, in a current power plant design, your waste heat is at fairly low temperature. We have an amazing thermal hydraulics team now, so we are actually interacting with many various companies that have very variety need of steam at different temperatures, so much electricity. So there's a lot of very interesting games you can play of where you take steam out of the turbine, etc. But in a standard application, if we're just trying to make electricity, we're much more efficient. Light water reactors are low 30%. The small PWRs are typically only 29 or 30%. That's where we're talking about our 50% improvement from like 29 or 30 up to 44% thermal efficiency. But on a simple power plant, the waste heat might have some district heating uses. But as I said, once you get into specific clients and applications, the sky's the limit. There's a lot of very, very interesting ways you can tap off steam. Some surprising results we found of how you can do things very efficiently when you're trying to do a mix of thermal and electrical. So I hope that helps.
Okay. And then we have two questions. I will shoot them the two together so you can answer them. So one is from Boris. It says low pressure equals how you deal with I guess xenon and krypton production, and the second one a bit different is when and where is the prototype?
So yes, off gases, all molten salt reactors will have xenon, krypton coming out. Some of the short-lived isotopes are going to give you quite radioactive daughter products. Usually it's the very short half-lives. Our philosophy has been we are a simple burner reactor, not trying to be a breeder. We don't encourage our gases to leave our core unit rapidly. We actually let them linger in the upper gas plenum for quite a while. So what is leaving at a rate of, I think it's something like 4 liters a day, it's very, very slow, is very old isotopes. So about the last of interest is a 10-year krypton, which is not too troublesome. It's dealt with. Actually, it's bled off at most reprocessing plants, but that very slowly leaves the core unit and is pressurized into gas bottles for storage with very low heat. So we prefer, instead of an elaborate off-gas system, we allow the off-gases to remain within the core unit. We actually get some of the heat back that way as well. So, I think the second was prototype. Our plan is to go to a commercial demonstration. There will undoubtedly be some differences, probably equipment that we might not need on the nth plant, et cetera, for the regulatory process. We will have a physics facility, either zero power or subcritical. That's still a work in progress. That can be used. That will be hot salt, neutrons flowing, so to speak. So that can be another way to look at a demonstration or prototype. But we do want to go to a commercial unit to start.
David, that's really great. Thank you very much for the presentation.